Hey, welcome back. And today we are going to look at a very interesting paper. It's called Well-Read Students Learn Better on the importance of pre-trained compact models. So basically, it's a very thorough study for training a compact model, distilled on compact models, and they do really a lot of experiments. And if you are kind of working on this kind of compact model for the deployment or for production usage, this paper is really for you and very informative. It probably will save you a lot of time to do a lot of experiments, and you can have a better direction, better sense of how to train a compact model. The compact model, I mean, is like smaller transformer models, not like those super huge language models. Those smaller transformer models is easier to deploy or do other use cases in the real world. And yeah, so what's special about this paper? They basically give you a guideline, give you a kind of lessons on how to train a competitive compact models, and they do a very thorough study on pre-train and distillation and maybe fine-tuning these kind of combinations. What kind of effect is that? And also the most important thing is they find out the model size and the property of unlabeled data, which is used for distillation or pre-training. Is very important for training a compact model, and this is really understudied in the previous years. They train 24 models to do this kind of experiments, so it's quite expensive study. By the way, I make deep learning explained video every week, so if you would like to receive more relevant videos like this, don't forget to subscribe, and your subscription is also my best encouragement to make more videos like this. So yeah, this work is done by Google Research. Very interesting work. So yeah, this is their some of their steps and their terminology, so we better understand it before we dive in. So this is the one step called pre-training. Basically, is you have the setup is you have a very large BERT, fine-tuned BERT on a downstream task. We call it teacher, and we want to train a student, which is smaller transformer models or whatever model you want, LSTM or something, either. So your first step, you would like to do pre-training on the unlabeled language model data. Can be anything. It's just need to be the language, your target language. You don't need to have any label. And then the second step is called distillation. Basically, is to use the teacher to generate soft labels, which I will cover later. Soft label, and the student will learn how to generate those similar distribution of soft label. So basically, learn the knowledge from teacher. And the last step is just fine tune on the hard label, just the traditional fine tuning. But this can be optional. Most important thing is you need to do pre-training and the distillation, and they will do a lot of experiment to find out what the best combination, what's the best sequential order to apply these techniques. So what I mean by distillation, it's actually quite straightforward. It's usually when we do the classification, if we use a hard label, it's just like this picture. For example, we do the image classification. The hard label just says this is a cat, and we will give the cat 100% probability. Then the rest of just 0. So it's one hard encoding. Either this true or false. Then you learn from label. Labels just say, oh, it's 100% cat. But there are a lot of dark knowledge. It's called, this is actually looks like cat indeed, but they have certain percentage can be dark because it's also look like dark compared to other things, and also can be lions, can be apple, but they have different probability. And if you want to learn, you want to train a smaller model to learn from the teacher, then if you learn from those hard label, you cannot learn this dark knowledge, which is this object. It has certain property that's similar to dark, and also a little bit similar to lion, and it's really not alike to apple. How to learn this kind of dark knowledge, those kind of details? It's learning from this soft label, pseudo label. Basically, when teacher do the prediction, teacher maybe give this kind of assign these probabilities to each categories, and the student also will need to learn how to generate a similar probability. Because if a student can learn this kind of probability, it can learn more things. If it's compared to you just learn from 100% cat and 0% to the rest of them, you basically just not learn too much other knowledge. So this is kind of what we call distillation. By the way, I have a video go through more details about distillation. I will put in the info card and the description down below. If you are interested, feel free to check it out. Okay, and then you may ask, what the loss function is like for the distillation. It's actually pretty straightforward. When you normally do the calculate the probability of a certain class, you put your classification projection layer to do the multiply with your hidden state from whatever neural network that you have. You apply softmax on that, then you have this probability. And the distillation loss function is basically to get this unnormalized probability that's processed before a softmax. Then we call this logits, and we want to calculate how different the big neural network, which is teacher's logits, is different from the student's neural network's logits. So if the logits is of the teacher and the student are very close, then you got less penalty, which means your loss function is smaller. Then it is our objective. We want to make them the gap between them as smaller as possible. In other words, we want to make the logits that generated from the students and the teacher as similar as possible. So it's the loss function. Just briefly walk through that. And as for what the teachers are and what the students are in this paper, they actually have two kinds of teacher. One is a BERT-based model, and another is BERT large model. Depending on what experiments they did, they use different teachers. And for students, it's always 24 students, which is different sizes of BERT. So this is what those 24 students look like. You have different depths from layer 2 to 2 layers BERT to 12 layers BERT. And from hidden state, this is a hidden state of BERT from 128 to 768. So basically, this is the depth of the neural network. This is the width of the neural network. So you have the shallow and narrow neural network, shallow and wide neural network here. And you also have deep and narrow, and a deep and wide neural network, depending on the setup you have. And this is the millions of parameters. So you have the smallest one is 4 million parameters, and the largest one is 110 million parameters, which is very similar to BERT base model size. And this is the speed compared to BERT large model. So for the smallest model, is basically 65 times as fast as BERT large model. For the largest students, is just slightly faster than the BERT large model. An interesting thing is definitely with the layer, if you reduce the increase the layer by 2 times, then the speed increase 2 times, and increase another 2 times, the speed decrease 2 times, another 2 times. So it's very straightforward, but the thing that I'm not really sure about is when they increase the hidden size, the speed also decrease when you increase the hidden size by 2 times, the speed also decrease 2 times. It's a little bit strange. I guess it's because the way they benchmark this is because the batch size maybe is large. So whatever hidden size you have, you already fill up your GPU memory. Otherwise, if you make sure this with batch size equals to 1, I don't think the hidden size will affect the speed that much. Okay, so this is just the inference time for BERT, and definitely inference time is super important for the real world use cases. We care about that a lot. If you are deploying something, you probably will like to look at that. And I think this is something that got overlooked in the research, in this research area. Okay. So this paper's main focus is to train the model that's running very fast in the inference time and without losing too much model performance, like F1 score. Okay, so well, let me introduce a little bit like data types. There are 3 different data types in this paper. The first one is unlabeled language model data, which is used to language model pre-training. It's not language model pre-training, it's for your model pre-training, and it's used language modeling as an objective function. And the second types of data is unlabeled transfer data. Basically, it's usually we use that as a like in domain data to let the teacher transfer its knowledge for the student, because like I mentioned earlier, for the distillation you don't need to have label. You just need to run your teacher one time on label data, and teacher will generate pseudo labels, soft labels. Student can just learn from that, so you don't have to have labels for transfer learning, distillation. That's the beauty of it, so that you can have much more data. And for the label data, it's just for fine-tuning. It's just a very straightforward fine-tuning, hard label fine-tuning. So these are 3 different data types in this paper. And because they also compare this work with some previous work, basically the 2 papers from last year. And those 2 papers from previous years all use like truncating technique. Basically, is they have the teacher, which is deeper neural network, 12-layer BERT, something like that, and they truncate the bottom of 6 layers, like bottom few layers from the large BERT. Let's say in the distill BERT, they truncated the 6 layers, bottom 6 layers of the large BERT model, and use that to initialize the student weight. And student is a 6-layer model. So this we call a truncating technique. And this is just terminology they use in this paper. And the problem with truncating technique is you have the assumption on teacher and the student's architecture. For example, in the distill BERT model, you cannot train a student that with different dimension size than the BERT teacher. And you also cannot have very different architecture. For example, if you want to train a LSTM student, you cannot do that, because you need to truncate. Basically, you need to get your initialized weight from your teacher. If your architecture is so different, you cannot do that. Okay, so this is some restriction for truncating technique. Okay, so the comparison is like this. This is just the Google's work, pre-train and the distillation. The first step is to pre-train your model, do language model pre-training on your compact students, not teachers involved yet. And the second step is to do the knowledge distillation, basically to use the teacher network to generate soft label and the student to learn from those soft labels. And this is definitely very, very flexible for your architecture that you use in the student neural network, because you can have whatever neural networks that you want. And for the work, there's a paper called by Sun, and it's patient knowledge distillation. The first step, they use they truncate the weight from the BERT-based model, and they use the patient knowledge distillation as a second step. And for this set work, it's a distill BERT from Hugging Face. They basically use the BERT, truncated the weight from the BERT-based model, and do the language model distillation. Basically, is to do the language model training, but with distillation as a objective function. Yeah, because in the language model, the objective is to predict the mask token, and in the distillation language modeling is basically to learn the distribution of the master tokens. It's not just predict the mask token. You need to learn the distribution. The teacher predict the mask token because, for example, your mask token is apple. Then teacher predict a lot of different probability of every vocabulary in this neural network. Then your student need to learn the distribution. So it's like the cat example that I showed you previously. Yeah. And the second step is to do the fine tuning on the distilled neural network. These are the differences between these three papers, and this is the like performance comparison. You can see for the patient knowledge distillation here, and compared to this work, this paper, and basically this paper has like a better performance, 0.5% average meta score than this patient knowledge distillation. 0.5% is not a lot, but it's like average from a lot of different data sets. So I will say it has some credibility. And yeah, because sample size is big, so the significance is like larger. And for the comparison with the distilled is basically 2% meta score higher than it. Is quite significant, I would definitely say. And so this just tells us like this pre-training and distillation, this combination probably very important, so give you more reason to keep watching this video. So they analyze three different tasks. One is sentiment classification. They have two different data sets, SST and Amazon reviews. For SST is binary, it's negative or positive. For Amazon, it's three ways. So it's negative, neutral, or positive. And another task is natural language inference. It's also three ways classification. Basically, give you two sentences. One is premise, and one is hypothesis. And you need to, the model need to classify if this is like these two sentences are entailment or contradiction or neutral. And the last task is textual entailment. It's basically very similar to natural language inference. Is to give you two sentences, and the model decides if these two sentences are entailment or non-entailment. Okay, so these are three different tasks, and they have basically 4 experiments. And first, let's just look at the sentiment analysis. For the label data, for fine tuning is SST 68,000 data points, and they use the movie reviews as unlabeled transfer data. They use this to do the knowledge distillation, which is the size is much larger than the label data. It's 1.7 million samples. And for book review, 50,000 samples, and they use the book reviews, other set of book reviews as unlabeled transfer data, 8 million, which is a lot. Okay, so for the rest of inference tasks, they have like this RTE is very small data points, and you have larger unlabeled transfer data, and like this natural language inference data set is a lot of data points, and also use the same natural language inference data set as transfer data. So this is set up. Also, the first question they want to answer is it enough to pre-train word embeddings? So what does this mean is to you use certain way to pre-train the word embedding layer in the transformer architecture, and use that to initialize your student's word embedding layer. And to answer that question, we need to know how they do that. It's quite interesting. How they do that is very straightforward. They pre-train the one layer BERT. It's the one layer BERT, definitely one BERT layer with one word embedding layers. Then after pre-training, then they discard the BERT layer and only keep the embedding layers. and use this embedding layer to initialize the word embedding layer in the student transformer architecture. Okay, so quite straightforward, and then we can see the answer for that question is no. I tell you first, and you can see this. The red line is the word embedding. They use the pre-trained word embeddings, and they do the pre-training, distillation, and the one in the gray line you can see is pre-training and distillation, but the difference is they initialize the weight from the 12-layer models directly. It's truncating technique, and you can see the performance of the truncated from the 12-layer models is much better than you only truncate the word embedding layers, and it's like very significantly better. So they have the conclusion: the word embedding layers only contribute to 24% of the truncating benefit. Basically, if you do the pre-training distillation and you use the word embedding to initialize that, your students' word embedding layers, you only can benefit 24%. But if you truncated all layers from a larger neural network model, then you can have 100% benefit, which is this line. But you probably see a green line. You wonder what that is. I will explain a little bit later. So is it worse? Second question: is it worse to truncate deep pre-trained models? So previously we truncate the word embedding layer only, or truncate all layers. For example, if student is 6 layer and the teacher is 12 layer, then we truncate the bottom 6 layers of the teacher. And compared to that, if we don't truncate any weights from the teacher, we just do the pre-training, distillation, will it be better than truncating or not? It's a question we want to discuss. Okay, so the green line is for that. Is we don't truncate any weights from that. We just randomly initialize the student and train the student model, pre-train the student model, do the language model pre-training on the language model pre-training data set, and they found out, oh, if you do language model pre-training thing and the distillation, you can find out, oh, your students like have a much better performance. Yeah, so the conclusion is, if you have enough data for language model pre-training, then you should always just pre-train your student instead of initialize your weight from the teacher's bottom layers. And definitely this difference is kind of narrowed down. This gap got close when the models also increase, the parameters of the model, student model increase. Okay, so this is some conclusion. Okay, third question: what is the best student for fixed parameter size budget? For example, if you want to train a student, maybe it's 100 or maybe 10 million parameters, then do you want to train a very deep neural network, deep and a narrow neural network, or you want to train a wide and shallow neural network? Okay, so the answer is you should prioritize depth over width. Always. The deeper neural network is always more powerful than the shallow but wide neural network. That's what I found. Actually, there are so many other studies also found this phenomenon. And also the pre-trained model, if you do the pre-training on your model, you will just have so much better performance than the model that is not pre-trained. By the way, you may be curious. Previously, when I show you data set, they have the label data set and a transfer data set. Then what's the data set they use for language modeling, pre-training? To be honest, I am still a bit confused from reading the paper, but I believe they use the transfer data set as a pre-training, language model pre-training data sets. This is my assumption. They pre-train the model and the transfer use the distill the model on the same data set, which is labeled as a transfer data set. Okay, so we want to know what does the model depth affect the model, and also what does the model width affect the model. Then we look at the left part of this graph first. You can see that they are all with the same width, with the same hidden size, but different layer, 2 layer to 12 layer. And the deeper model is, the better performance is. This is straightforward. And also this trend, if you compare the model, they maybe have a similar parameters, but with a different depths of the neural network, then definitely you will always see the deeper model is better. And in this graph, another thing I want to point out is the pre-train and the distillation, which is the proposed method in this paper, is always better than the pre-train, fine-tuning, or distillation alone, or you just do the basic training. The basic training is just use the label data and you train your student model from scratch. It's not student model because it's not learning from teacher. You just train your compact model from scratch with the hard label, and the performance is just quite bad. And even you increase the number of parameters in your model, then your performance is still pretty flat. It's just not much different from the tiny model, like this BERT large model. Yeah, this BERT based model, it's just not different from the tiny BERT. So if you just do the straightforward pre-train, you should do the straightforward training on your label data. You don't need the large model because the performance is just not much different. And if you do the pre-train and the distillation, definitely when your model size is getting bigger, your model will be more expressive, more powerful. Okay, so this is SST2 sentiment classification data set, and this is some results from natural language inference data sets. As we can see, the pre-training and the distillation is always better than pre-training and the fine-tuning, but the gap is not that big in MNLI data set, but still much better than distillation. Distillation is just you do the distillation on your transfer data set without fine-tuning, and definitely the performance will be worse than the previous two methods. And the basic training is consistently perform worse than the proposed method here. It's quite a lot worse. It's like 15% accuracy or F1 score lower than that. And for the RTE dataset, which is have very limited label data, so definitely if you just do the basic training, your model performance is pretty bad. You do the pre-train and distillation, and performance is so much better. But the gap in this dataset and these datasets are quite different. This is interesting. It's definitely related to the property of the dataset. I think I can explain that a little bit, because the label dataset in this RTE is just 2,000 something, so fine-tuning cannot have too much impact. But in this dataset, you have much more data points, so fine-tuning will make your model performance much better. So definitely, if you are working on a task that have a lot of label data, then pre-train and fine-tuning is not necessarily worse than pre-train and distillation. I mean, yes, if you do the pre-training and the distillation, and then you do the fine-tuning again, then you will have definitely the better performance. But they don't show too much the comparison for that method. Okay, so this is for SST2, and the gap between pre-train distillation and pre-training plus fine-tuning is just huge here. and not to mention compared to the other data set, like the basic training is always like have low 80 performance, but the pre-train and the distillation have almost close to 95%. I believe it's accuracy. Okay, then for the Amazon book reviews, three-way sentiment classification. It's very interesting when the model size is like mini, 2 layers and 256 hidden size. It's just to recover to the teacher's performance if you do the pre-trained distillation. Well, this is crazy. And even when you increase the model size, the performance is even better than the teacher, which is unimaginable. It's interesting. Yeah. And for the other trend, always this is quite weird because only in this data set the distillation only is outperforming the pre-train and the fine-tuning. This is a little bit weird, but it just it is. I don't know how to interpret that. Maybe you can come up with some explanations. So this is Amazon book reviews, which is three-way sentiment classification. Three-way, and yeah, this is the data set that we want to discuss how much the transfer set size will affect the model performance. So they have because you know the transfer data set in this setting, they have A mediums data points to the model learn from the teacher, and they just do the data ablation. The first is data point is like they only feed 50,000 samples to distillation, and keep increasing the size, and in the end it's A medium samples, and you can see that if you have big enough transfer data set, your pre-trained distillation model will recover to teacher's performance completely, roughly after 5 million mark. Which means if you want to train a compact model, then you also have a lot of in-domain data as a transfer data set, which is unlabeled data, but it's in domain. Then you can distill, pre-train your model, compact model, and distill your compact model from learning from teacher. Then you end up will have the model that have almost the same performance as its teacher, which is maybe 2 times, 3 times larger neural network. Yeah, so let me materialize this a little bit. Okay, maybe let's say if you are in the biomedical domain and you want to train a BERT model, transformer BERT model, maybe 6 layers or 3 layers, and you have a lot of biomedical in-domain text, but without labels. Let's say you have 10 million. Then what you should do is you should pre-train your transformer model, smaller student model first on your biomedical text. And the second step is to do the knowledge distillation, let the teacher to run the unlabeled data and label that, put a soft label on that, and let the student neural network to learn that. Then you have like 1/3 or like even 25% of the size of the model compared to your teacher, but with the same performance. This is, I think, very important lesson or insight to learn for the real-world application. In the next experiment, they want to explore how much the domain shift will affect the model. And is the model robust enough to resist this kind of domain changing? Okay, so first of all, a lot of research actually point out that out-of-domain data will degrade your distillation results. It's like if your data they use to do the knowledge distillation is too far away from your downstream task, then your model will probably end up like getting worse performance. So in order to make sure this, they propose I use a way to make sure the Corpus similarity. Basically, it's to use the correlation coefficient to make sure how different these two Corpus are, or how similar they are. The way they make sure the similarity between Corpus is like this. So basically, they find out the most common words, top 100 most common words in two Corpus, and calculate the difference between the same words they rank in different Corpus. For example, if apple rank in the Corpus X, maybe number 1, and it's 50 is most common in the Corpus number 2, which is Corpus Y, then their difference is like 50 minus 1, so it's 49 here. Then you use this formula to calculate the score, the similarity score. The higher means these two Corpus are very, very alike. So how to interpret this formula? It's actually quite straightforward. If the difference D is a lot, then your similar score will be very, very less, because the larger D is, the smaller score will be. And also, if the rank of the term, for example, we want to measure Corpus X and the Corpus Y, then we use Corpus X as a anchor point. Then apple, the turn apple is here, because turn apple is very important in the Corpus X. So apple's weight will be a lot. You see, if the rank of the word is like lower, then n will be larger, then the weight of this will be smaller, because it's a denominator here. Okay, so you roughly get the idea. They have the different importance score for each term. Then depending on the rank in the Corpus A and the Corpus B, if the terms a lot of common words and they also rank very similar position, that means these two Corpus are very alike, which is very, I think, straightforward. If you are doing some biomedical domain things, maybe you make sure how different biochemistry papers Corpus are from the maybe bio informatics, this kind of Corpus. They supposed to use a lot of words they are very alike, and also the most common words, top 100 most common words are very similar, and they rank very similar as well. If you compare bioinformative domain to maybe physics domain, then the most common words they use will be very different, and the rank will be also very different. Then you can make sure by this score. I think that's super interesting thing, and maybe a lot of people also encounter how to make sure the Corpus similarity, and you can try to use this method. Okay, so they use the Amazon book review as example, and so first of all, they select one is Wikipedia, very general data, and they make sure the domain similarity that between Wikipedia and the Amazon book reviews, and the correlation efficiency is 0.4. And another is unrelated product category. It's product review, but it's totally different domain, and the similarity is like higher, 0.5. Another is movie reviews. It's quite similar to book reviews, but just the related product but it's not exactly the same. The similarity goes higher, 0.76. And another is just in domain data book reviews as well. So they use this to do a distillation and pre-training and distillation, and or pre-training with plus fine-tuning. And you can see that if you use the Wikipedia, which is out of domain data, then for distillation only, you will have the worst performance compared to the basic training. But if you use Wikipedia to do the pre-training distillation or pre-training distillation plus fine-tuning, then your performance is still better than baseline. So which means even sometimes you don't have like in-domain data for distillation, then you can still use Wikipedia, so long as you pre-train on that and also do the distillation on that. And if you have the more similar data, like unrelated product category here, then even just use the distillation, your model performance will outperform the basic training. And definitely for sure, when the similarity gets higher, like movie reviews, then model's performance goes higher as well. And the book review is in-domain data, so definitely your performance is much better than the base training. And another baseline I would say is also important to look at. It's pre-training and fine-tuning. This one, yeah. So even you don't do pre-training and the fine-tuning, you just do the distillation alone, your model can outperform the pre-training plus fine-tuning if your distillation data is similar to your downstream task data enough. So that's inspiring, I would say. Yeah, we have reached the end of today's video. And what's the takeaway today? Takeaway is, if you want to train a compact model, smaller model, even you only have the label data set, you should always do the pre-training on the data set and do the distillation. You will have, most likely you will have a better performance compared to you just train from scratch on the data set. And definitely if you have more unlabeled data for the distillation and the pre-training, the better. That's the way how you can train a very competitive compact model. If you enjoyed the video, give it a like and don't forget to subscribe for more relevant deep learning videos like this. And other than that, take care. Until next time.